Okay, this is going to be a video lesson over the binomial theorem, which is our only lesson from chapter 8 that we're doing in this unit. We'll do one or two more from chapter 8 after this test. This is lesson 8.5 out of the Blitzer book. I've got, I did it again. I forgot to number the bottom half of the page, but I've got a list of problems for you here. We're going to start with, we're going to skip that first section. I don't know what those are yet. We're going to go to number 9. Number 9 says you've got x plus 2 cubed. And you may be thinking, what on earth is new here, right? You can FOIL all day long. You've been doing this for 1,000 years, okay? You would hopefully, I think your approach would be to write this as x plus 2 times x plus 2 times x plus 2, right? And you would FOIL two of them, which would give you x squared plus 4x plus 4. And then you'd still have an x plus 2. And you FOIL that and you get an x cubed plus 4x squared plus 4x plus 2x squared plus 8x plus 8. Combine like terms, I'm getting x cubed plus 6x squared plus 12x plus 8. Okay? Now you can imagine that the higher the power on this binomial, the messier this is going to get. Okay? Cubing it is about as far as we ever really want to go with FOIL. If I made that to the 4th power, you add on another x plus 2, 5th, 6th, 7th, and so on. By the end of this lesson, what we want to be able to do is something like x plus 2 to the 15th power, right? And right now, that would take 1,000,000 years. What we can do, though, is we can try to establish a pattern. And it turns out, and for the sake of brevity, I'm skipping to this, there was a mathematician a long time ago whose last name was Pascal. I can't remember his first name, so we're going to call him Pedro. Pedro Pascal, hopefully you think that's as funny as I do, created something called Pascal's triangle. And he said, what if you started with a 1 at the top of a triangle? And then you in the second row, you would take this number plus this number, right? So there's nothing here, plus 1 would give you 1. Nothing plus 1 would give you 1, right? And in each new row, you're going to have one more number of elements, okay? So now I'm thinking 0 plus 1 is 1. 1 plus 1 is 2, and 1 plus 0 is 1. And you can see you're always going to have 1s on the outside, but then you're going to have 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, right? And you can see each each number in Pascal's triangle is just the sum of the two numbers that straddle it, essentially, right? So you could generate this on down forever. That's as far as I need to go. But it turns out that these can give you the coefficients of a plus b to the n power, okay? Now, it's not obvious. I'm going to pause this for a second while I get a formula copied down. Okay, So hopefully you can see here, I've just basically distributed out a few powers of a plus b. A plus b to the 0, anything to the 0 power is 1. Right? To the first power is just itself, but you'll see I've written in the coefficients the understood 1. So a plus b to the first power, that's 1a plus 1b. A plus b squared is 1a squared plus 2ab plus 1b squared. That's the perfect square pattern. A plus b cubed follows the pattern of the first example that we did. 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. I hope you're seeing the 1, the 1, 1, the 1, 2, 1, the 1, 3, 3, 1, right? It's that pattern there. So the coefficients of your expansion, of your binomial expansion, correspond to the n plus 1th row of Pascal's triangle. So if you are raising your binomial to the 4th power, you're going to go to the 5th row of Pascal's triangle, because Pascal's triangle starts at 0, not at 1, in terms of degree. Right? So in this case, a plus b cubed, its coefficients 1, 3, 3, 1 come from the 4th row. 3 plus 1 is 4, right? Okay. So if you've got Pascal's triangle, right, copied down in the margin of your test, maybe down 7 rows or so, who knows, then if you copied it down 7 rows, then you could do any binomial expansion up to the 6th power, right? So you can, as many rows of Pascal's triangle as you can make, right? You can raise a binomial to 1 less power than that. This is pretty powerful, but you might notice that Pascal's triangle blows up as we get bigger. So let's do an example or two doing it this way, and then we'll see if we can make the process just a little bit more efficient. Let's see. Yeah, I think we have space over here. Let's switch colors. Okay, so let's start with example 10. It says x plus 4 cubed. So if I'm cubing, I know that I'm on the 4th row of Pascal's triangle. I'm right here. So my coefficients look like 1, 3, 3, 1. And then this is where it's not as obvious, but once you've seen it a few times, you can put these together really quick, okay? You're going to have an x and a 4 in all of those terms. I just put them in parentheses. Okay? The x's are going to go in descending power from the maximum power, which is a cube in this case. 3, 2, 1, 0. Okay? So our first x is cubed, the next one's squared, then we have just the first power and then to the 0 power. Okay? The 4s are going to do the same thing coming back this way. 3, 2, 1, 0. Just add all of these up. Okay? And we can simplify this a ton. So 1x cubed times 4 to the 0, that's just x cubed, right? Because 4 to the 0 is 1, and 1 times 1 is just 1, okay? And plus 3, well, let me not get ahead of myself. I've got a 3 times 4 to the first, that's 12, and then an x squared. And plus 3 times x times 4 squared, which is 16, so 16 times 3, I'll just do over here. Okay, so that's 48. So we're looking at 48x here. And then 1x to the 0, 4 cubed. 4 cubed is 64. And then x to the 0 is 1. So all we have there is 64. Right? That's how you can do a binomial expansion with Pascal's triangle. It's pretty fast. Let's see if I can hold your attention for one more. Doing okay on time. Let's look at what would be example 11. 3x plus y. Ooh, you know what? That one's cubed. I want to do something a little bit more interesting. So let's go down to what would be example. Let's see, this would be 11, 13. This would be example 15. And it's 2x plus 1 to the 4th power. Okay, so this is where you have to be careful and you have to sort of account for all of the pieces and put them in their proper place. But this is my a and this is my b, okay? I'm raising it to the 4th power, okay? So I know I'm on the 5th row of Pascal's triangle. So I need a 1, 4, 6, 4, 1. Those are my coefficients. 1, 4, 6, 4, 1. Hope I left myself enough room there, okay? Then each one of them is going to have a 2x and a 1, a 2x and a 1. Okay, the 2x's are going to decrease in power, right? From right to left, or left to right, my bad. And the 1's are going to increase in power, okay? Now you may already be saying 1 to any power is still 1, and that's fine if you know that. But if you don't, you want to go ahead and go through this step, okay? So the 2x is going to start off to the 4th, then cubed, and squared, into the 1st, and the 0. The 1's are going to go from the 4, 3, 2, 1, 0. And then we just add these up and simplify. Okay, so 2x to the 4th, okay, that's 2 to the 4th, x to the 4th. 2 to the 4th is 16, okay? Everything else is 1s, so that looks like 16 x to the 4th. And here I've got a 4 times a 2 cubed times an x cubed. 2 cubed is 8. 8 times 4 is 32. So I'm looking at 32x cubed. The 1's, none of these 1's are doing anything for me, okay? So I can basically ignore them, okay? Then 2x squared, that's 4x squared because the 2 is getting squared as well. So I got 4 times 6 is 24. 24x squared plus then just 8x. And then this term right here is just 1. Right? So that's a full binomial expansion to the 4th power of 2x plus 1. So the moral of the story, I'm going to erase this bit in the middle here. Okay. A plus b to the n is going to follow the pattern, okay? Your coefficient from Pascal's triangle, right? So from the n plus 1th row, I'm just going to call that coefficient, I'm going to call them c's for now. We're going to have a better way to write them in a minute, but for now, I'm just going to call them c's, okay? So c, whatever your coefficient from that is, and you'll have a to the n, b, to the 0, right? Then plus, if that was your c naught, then now you'll have c1, a to the n minus 1, b to the 1st, right? Plus c2, a to the n minus 2 power, b squared, all the way down to c sub n, a to the 0, b to the n. So your a's are decreasing in power from your maximum, and your b's are increasing in power to your maximum. That was that wraparound thing. So we took, in the problems, we would take the first section of the binomial, the first term, right? And we would exponentiate it starting at n and going all the way down to 0. Then we would take the b and exponentiate it starting at n, going down to 0 the other direction. And you can see that at play in this formula. All we're missing is, right, at the moment, these c's, these coefficients, they have to come from Pascal's triangle. And the question is there an easier way to generate them? And the answer is yes, okay? Well, easier is a strong word. Definitely faster, especially once you get down to deeper rows of Pascal's triangle. So let's get rid of Pascal's triangle for a moment. And let's just ponder. This is a bit of a probability question, okay? I'm going to give you the quick version because I'm running out of time to film this video. Okay, I've got 4 markers here, okay? How many ways can I, out of these 4 markers, take 3, okay? So it's 4 things taken 3 at a time. How many ways are there to do that, okay? Well, that's pretty easy because I can take all but the red, I could take all but the purple, I could take all but the green, I could take all but the blue. So that's 4 ways, okay? What would be a much more difficult question is how can I take these 4 markers 2 at a time, okay? I can take these 2, I can take these 2, I can take these 2, or I can take these 2, and the permutations continue. What's that exact number? Well, you don't want to have to test it empirically every single time. So it turns out in mathematics we have a notation for this. It's the combination of n things taken r at a time. N take r is how it reads, and this is a probability concept, right? N take r. Another way of writing this, and this is how you'll see it in your book, is vertical parentheses in r, okay? The combination of n things taken r at a time. We are going to dive into combinations and permutations deeper after this exam. For now, all you need to know, and I'm looking at the textbooks, I want to make sure I get this right, okay, is that the binomial coefficient that you're using in any given term is equal to, so say you've got a plus b to the n, right? We did this a second ago. Your first coefficient is going to be the combination of n takes 0. And you're going to have a to the n, b to the 0. Then your second coefficient is going to be the combination of n minus 1. Take 1. I'm already wrong. The top stays in. My bad. Okay, the top of the combination stays in, which makes sense if you think about it. I don't know what I was doing, but the number of things, right, is not changing. The maximum power of the polynomial is not changing. How many you're taking is what's changing, okay? So essentially, the numerator of your combination is the power that you're raising this to, right? That never changes. And then the bottom, the denominator, that's air quotes because it's not actually a fraction, right, is equal to the row of Pascal's triangle that you're on. You can think of it as n plus 1, right? The 0 is like the first row, 1 is like the second row, right? And so then here in your second coefficient, you're going to have a to 1 less power, b to 1 more power, then all the way down to the combination of n take n. Or do you stop at n minus 1? No, yeah. Okay. Of a to the 0, b to the n. Okay? And that's going to be your general formula for the expansion all the way down. You add all of those up. So that's all the time I've got, but there is a button on your calculator to calculate a combination. We'll learn a formula for it later, okay? But if you're in your calculator, you go to probability, which is math over prob, and then down there's NCR, all right? That's the combination of n things taken r at a time, and you can enter those little subscripts. So it follows this notation, right? So say, here in this example, I wanted to find this coefficient here. I know it's 3, right? But for me, it's the combination of n, which is 3, taken 0, 1, 2 at a time, and of course, that gives me 3, okay? So if you're doing very high powers on your binomial expansion, you don't have to resort to Pascal's triangle. You can use the combination formula to find those coefficients. I was a little rushed for this video, so I hope that makes sense. If it doesn't, please email me with questions. You've got almost half of your homework is just these combinations, right? You can use your calculator for these, or if you want, you can draw out Pascal's triangle and figure out which numbers they correspond to, if that's more your persuasion, okay? And then this bottom half is just binomial expansions, and that's all there is to it, okay? Expand some binomials, and that'll be it for this unit. That's the last thing that's on the test. Everything else is solving system of equations with Gauss-Jordan and Cramer's rule, okay? So Gauss-Jordan, Cramer's rule, and binomial theorem, okay? That's it. That's all I got for you.